this is K Devender Reddy, Assistant Professor in Department of Electrical Engineering. In this video, we are going to discuss about how to draw a circle diagram and how to determine circuit parameters, that is equivalent circuit parameters of induction motor from the circle diagram we have to see. The following test data that is required for drawing a circle diagram, that is no load test, block rotor test and resistance test. These three test data is required for constructing the circle diagram or for drawing the circle diagram. That is no load test data, block rotor test as well as resistance test. So from the no load test, we have to record no load voltage which is required, that is V0, and no load current required to meet the constant losses, that is I0, and no load power, that is to meet the constant losses, that is equal to W0, or you can also represent with the letter called P0, that is no load input power for induction machine. So these values represents the no load quantities when you run the induction motor under no load case. When you run the induction motor under no load condition, the amount of voltage which is required to run the induction motor at a rated speed, that is called as no load input voltage of induction motor, that can be represented by V0, and the amount of current which is required to develop the magnetic field and as well as to meet the constant losses, that is called I0, and the amount of power which is consumed in the induction motor under no load condition to meet the constant losses of induction motor, that is represented by no load power input to the induction machine, that is P0. So these are the three values we have from the no load test on induction machine. We have to run the no load induction motor under no load condition. We have no load voltage V0, no load current I0 as well as the no load power P0. From these values, you have to calculate no load power angle, that is phi naught is equal to P0 by root 3 times of V0 I0, that is equal to no load input power divided by root 3 times of V0 no load input voltage as well as the no load input current for induction motor. So this is a case from the no load test. We have to record the meter values, that is called the no load parameters V0, I0 as well as the P0. From the test data, you have to calculate the no load power angle, that is called phi naught, which is equal to P0 by root 3 times of V0 and I0. And similarly, from the block rotor test, that is you have to block the rotor of induction motor completely and apply the voltage, reduced voltage you have to apply to the induction motor, so that the rated current is circulating, the rated current is injected, the rated current is circulating in the armature, that is called the stator of induction motor. So the amount of voltage which is required to circulate rated current in the induction motor is called as short circuit voltage VSC. And similarly, the rated current under the short circuit condition we can naming as ISC, short circuit current of induction motor. And the amount of power which is consumed in the block rotor test is called short circuit power PSC, which is majorly the variable losses called as copper losses. And the block rotor test, your friction and windage losses anyway is 0 because the rotor is not rotating here. The amount of power which is consumed under block rotor test is only to meet the copper losses, and in addition to the copper losses, some amount of hysteresis and eddy current losses also there are also included in PSC, but which is negligible quantity because these losses, that is hysteresis and eddy current losses, were depending upon the voltage. But in the case of short circuit test, that is called a block rotor test, the amount of voltage we can apply it is very less, that is around 20 to 30% of the rated voltage. So that is why we neglect the losses which is included in the wattmeter reading under block rotor test. Similarly, in no load test also, the P naught is not only the no load losses, which is also having some sort of copper losses which are included in the induction machine, but that are very negligible because the copper losses are depending upon the current, depending upon the current input to the induction machine. So the no load current is less, then we have to neglect the copper losses under no load test. Whereas in the case of the transformer as well, we are not considering the losses. But in the case of induction machine, if you want to more accurate results, we have to consider no load copper losses under no load test, because the no load input current required for induction machine is 30 to 40 percentage of the rated voltage, rated current, 30 to 40 percentage of rated current. So to get more accurate results, you have to consider the no load copper losses, and you have to subtract that no load copper losses from the no load power input to the induction machine. Then you will get the more accurate results than without considering the no load copper losses of induction machine. But in the case of block rotor test, we don't want to consider the hysteresis and eddy current losses, and that means comes into the constant losses category. Both friction and windage losses, all these friction and windage losses anyway zero in the block rotor test, because the rotor is not rotating, it is completely blocked or completely blocked, so that your friction and windage losses anyway it is zero, and even the hysteresis and eddy current losses may be present, but which are depending upon the voltage. That is why we are not considering the iron losses in the induction machine under block rotor test. So from this test data, you have to calculate phi SC, that is a short circuit power angle, that is a phase angle under block rotor test. Phi SC is equal to PSC by root 3 times of VSC into ISC, and you have to calculate ISN, that is called ISN is nothing but short circuit normal current, short circuit normal current, short circuit normal current. That is nothing but under short circuit, that is under block rotor test, if you apply the rated voltage, only the reduced voltage can causes the flow of rated current, that is called ISC. But in that case, if you assume under block rotor test, if you apply a rated input voltage to the induction motor, the amount of current circulating in the rotor, the amount of current expected to circulate in the rotor is called as short circuit normal current. That is the current which is circulating, expected to circulate in the stator of induction motor when you apply the rated input voltage, that is equal to ISN is equal to ISC, that is a short circuit current into V naught by VSC, that is no load voltage by short circuit voltage. This will gives you the amount of current which is expecting, or we are expecting to circulate in the stator of induction motor when you applying the rated voltage, rated input voltage under short circuit condition, that is called under block rotor condition. The power input to the rated voltage, the power input at rated voltage under block rotor test. Similarly, like in ISN, we have a PSN, short circuit normal power, which is equal to PSC into V naught by VSC whole square. This is the short circuit normal power under block rotor test. We are expected to consume the amount of power which is consumed in the short circuit normal voltage category, that is PSN equal to PSC into V naught by VSC. And these are the things we have to calculate before drawing the circle diagram, or before start drawing the circle diagram. We have to calculate phi SC, short circuit under block rotor test phase angle, phi naught under no load test phase angle, ISN short circuit normal current, as well as the short circuit normal power under block rotor test. These are the things we have to calculate before drawing the circle diagram. Later, we have to follow these steps how to draw the circle diagram. That is, I am directly explained. You can refer this PPT. I'll clearly giving 7 to 8 steps. I I think 13 steps I am given. So how to draw and how to find efficiency, how to find sleep, and how to find torque, everything from the circle diagram, how we can find. I will give you the detail. I will clearly mention here in the PPT, that is 13 points. I directly explain how to draw the circle diagram from the given test data, that is called no load test data, block rotor test data, as well as the rotor, as well as the resistance test data. That is, we have to measure the resistance of the stator with the help of either multimeter, or you can also conduct a DC resistance test by connecting a simple voltmeter and ammeter. Generally, we know that is a volt ampere method to calculate the current of the any winding. Let us first of all draw the coordinates x and y axis. This is y axis vertical, and this is horizontal axis x axis. First of all, we know I naught, and we know ISN, we know phi SC, and we know phi naught. These are the things we know. You already calculated. First of all, draw no load current I naught. First of all, draw no load current vector I naught. Before drawing the no load current vector, you have to scale. You have to write a scale. I am assuming on x-axis 1 centimeter is equal to 2 ampere, for example, or 1 unit of the x-axis is equal to 2 ampere. Let us now draw a I naught current vector, that is no load input current vector, from the origin with respect to the y-axis with an angle called phi naught, that is no load power angle, that is no load phase angle between V naught and I naught. So this is the curve we have, the black color line. This black color line is a I naught, which is drawn from the y-axis with an angle phi naught, and this length of the OA vector, that is called no load current vector, is depending on the magnitude of this current. For example, if the magnitude of I naught, for example, I am assuming it as, for example, it is a 4 ampere. That is, I am assuming. If the magnitude of current, no load input current to the induction motor is 4 ampere, so the on x-axis 1 centimeter is equal to 2 ampere, so it is 2 centimeter length line. So we have to draw from the origin the 2 centimeter line. So length of the OA must be is equal to 2 centimeter, because it will be of 4 ampere, and 1 centimeter is equal to 2, 1 centimeter of the x-axis is equal to 2 ampere, so it will be 2 centimeters. So we have to draw a 2 centimeter length line from the origin with respect to the no load power angle or no load phase angle, that is phi naught. This is straight. From the y-axis, we have to draw a 2 centimeter length line when I am assuming it is a 4 ampere. For your understanding point of view, I am assuming the values here, that is no load input current is 4 ampere. So we have to draw, that is OA vector represents no load input current for induction motor. That is step 1, draw no load input current vector. Second step, draw ISN, that is short circuit normal current. Draw short circuit normal current vector with an angle phi SC, with an angle phi SC. So similarly, draw first we have to find ISN, that is short circuit normal current. Let us, I am assuming it is, for example, 20 ampere. I am assuming for example it is 20 ampere is the short circuit normal current of the given induction motor. And now draw ISN from the origin. Draw ISN from the origin with respect to the phi SC angle. With respect to the phi SC angle, from the origin, draw ISN line, which is of with an angle phi SC from the y-axis, and length of that line, that is ISN, is depending upon your scale of the x-axis. And 1 centimeter is equal to 2 ampere on x-axis. So the scale, according to that, ISN will be is equal to 20 ampere, that is 20 by 2. It is 10 centimeter length line. We have to draw a 10 centimeter length line from the origin with respect to the phi SC, that is called as ISN. This is a line from origin to S. For example, this is a point where it will be end, that is called as OS. The length of the vector, length of the line OS represents the short circuit normal current, which is equal to 10 centimeter. It must be 10 centimeter because our short circuit normal current magnitude is 20 ampere. So accordingly, depending upon your values, you have to draw short circuit normal current from the from the origin with respect to the phi SC angle from the y-axis. We have to draw which meet at the point of S. That is step number 2. Third step, from point A, this green color line, from point A, draw a line which has to be joined the point S as well as the A. From here, draw a line, simple line, which has to be joined these 2 points, that is point S as well as the point A. Third step, draw a line from point A to point S. Just simply join these 2 points. That line we can naming as output line of the induction motor. Output line of induction motor. After that, you have to draw a line from point A. From point A, draw a straight parallel line for x-axis. From point A, draw a parallel line for x-axis, straight parallel line for x-axis from point A. That is the next step, fourth step. After that, from point S, drop a line to the x-axis. From point S, drop a line to the x-axis which intersect your x-axis at a point M, let us assume. So I am drawing a line, which I am dropping a line from point S to x-axis, which meet your x-axis at point M, and which meet your another line that is called as AB. Let us, I am assuming the line is the AB line at point L, and length of the LM represents constant losses. Length of the LM represents the constant losses in terms of the centimeter. Then later we will discuss how we will convert these losses in terms of centimeters into watts by calculating the power scale of induction motor. That is a later part. First of all, we have to finish the construction of how to draw the construction of the circle diagram. Later we will find out power scale. That is the next step. After dropping a line from the point S to x-axis, which meet your x-axis at M point and which meet your parallel x-axis at point L. Then after, we have to locate a point on SL. That is actually the length of SM. Length of the SM represents the total input power drawn from the supply. Total input power drawn from supply under short circuit normal condition. Total input power drawn from the supply under short circuit normal condition. That is, it has under block rotor test, it has the total input power has to be meet the stator copper losses as well as the rotor copper losses and fixed losses. That's it. The losses which will be having under the block rotor test only to meet majority copper losses, and we are neglecting actually, but the fixed losses are also involved in that. When VSC, when reduced voltage you are applied, that fixed losses we can neglect. But under short circuit normal category, under block rotor test, if you are applying the rated terminal voltage, rated no load input voltage, then you have to consider fixed losses which has to be involved in the PSM. So length of the SM represents the total input power drawn from the supply under block rotor test when you are applying the rated no load input voltage to the induction motor. So the length of the LM represents the constant losses and the length of the SL represents the variable losses, that is both rotor copper losses as well as the stator copper losses. Now we have to split that losses into rotor as well as the stator separately. We have to split the total losses into rotor copper losses as well as the stator copper losses separately. This is how we can divide the total copper losses into stator as well as the rotor. This is depending upon the type of the induction motor it is. The type of the induction motor it is. Whether it is a squirrel gauge induction motor or a slip ring induction motor, we have to know. If it is a slip ring induction motor, by default we can split the entire losses into equally half of for each circuit, that is half for rotor copper losses and half for stator copper losses. But if it is a squirrel gauge induction machine, we have to find or we have to divide the rotor losses and the stator losses by a proper proportion, by a proper value that we have to calculate. See, under squirrel gauge structure induction motor, the rotor copper losses, ratio of rotor copper losses to the stator copper losses or stator copper losses to the rotor copper losses, whatever, ratio of rotor copper losses to the stator copper losses is equal to ratio of the rotor copper losses. We don't know the rotor quantities, we know the stator quantities only, that is total losses, total copper losses minus 3 times of I1 square, that is the stator current square, into RA square. Sorry, RA. Rotor copper losses by the stator copper losses is equal to total copper losses minus 3 times of I1 square RA. That is, we can represent, for example, rotor copper losses by SK and stator copper losses by KL. SK by KL is equal to, this is SK. Total copper losses will be split into SK by KL is equal to stator copper losses are, we can, no, sorry, this is the wrong way to calculate. For example, ratio of rotor copper losses, ratio of rotor copper losses divided by stator copper losses is equal to SK by KL, which is equal to stator copper losses we can directly measure, that is 3 times of I1 square into RA, and rotor copper losses is equal to total copper losses minus total copper losses minus stator copper losses. So by this formula you have to calculate ratio of SK by KL. By this formula you have to calculate ratio of SK by KL, and according to that value you have to split into two halves. You have to split into two parts, that is length of the SK represents the rotor copper losses and the length of the KL represents the stator copper losses. So after identify this point, that is K, then you have to draw a line between A to K. This is a line. You have to simply join irrespective of the angle just by an line you have to join, a straight line you have to join between point A and point K, that represents the torque line. AK represents the torque line and AS represents the output line. After identify the point which is dividing the both the losses in total losses into rotor copper losses and fixed losses. Then after find out center point for circle. Find out center point for circle. So to find out the center point for circle, you have to draw a bisector. You have to draw a bisector for output line. Next step, we have to draw a bisector line for output power line. That is AS. You have to draw a bisector line for AS, that is output line, right? So by taking more than half of the radius, you can draw here and here two curves, and here and here two curves that intersect your AB line at a point called C. That intersect your AB point at a point AB line at a point called C. That is acts like a center for circuit. So by C as a center and A as a radius, by C as a center, A as a radius, draw a semicircle. So this is the semicircle. By C as a center and A as a radius, CA as a radius, draw a semicircle. And if your calculations are right, if your calculations are everything is right, the point S must be on the circle. If your calculations are right, the point S must be on the circle. On the circle. If your calculations are wrong, the point may not be on the circle. It may be out of the circle or it may be inside the circle. That shows your calculations are wrong. If it will be on the circle, that shows it your calculations are right. So this is a way we have to draw a circle diagram. How to draw the circle diagram? That's it. After that, we have to calculate. The rest of the parameters which is required under full load conditions. That we have to know how to find out the slip, how to find out output power, how to find out torque, how to find out rated power output, how to find out the power factor. All these things at any point of the load we can find out. At any point of the load we can find out all the circuit parameters, all the parameters, whatever we required by the circle diagram. So this is the half of the point is completed, half of the portion of how to draw the circle diagram is completed. The later part we can discuss how to find the torque, how to find out the power at a rated load condition, and how to scale your power axis, that we have to discuss. For example, I am assume the motor is 5 HP. Motor is 5 HP. Convert into watts. 5 into 735.5, for example. How much it is? Around 3,900 watts. Is it right? 35 plus around 4,000. Let it be, I am assuming it is around nearly equal to 4,000. Make it as a round figure for easier calculation point. Assume it is around 5 HP and the equivalent wattage is around 4,000 watts. I am assuming. So why am assuming this 5 HP rating machine is to how to find the power scale, for example. So this is 4,000 watts, right? Now length of SM, length of the SM is nothing but total power total power drawn from input under block rotor test, under block rotor condition by applying rated no load voltage. That is nothing but length of the SM represents the PSN. Length of the SM nothing but PSN, short circuit normal power. For example, I am assuming the short circuit normal power is 10,000 watts. I am assuming it is, for example, 10,000 watts, and the length of the SM will be, for example, I am assuming length of the SM is equal to 10 centimeter. So now divide this PSN, that is 10,000 watts, by 10 centimeters. This is 1000 watts per centimeters. That is on the vertical axis, that is called the power axis. Power scale is equal to 1 centimeter on y axis, that is on vertical axis, which is equal to 1000 watts. 1 centimeter is equal to 1000 watts. Similarly, find out constant losses, that is length of the LM. Length of the LM, for example, it is 2 centimeters. Then 1 centimeter equal to 1000, it is equal to 2000 watts. Nothing but the fixed losses is equal to, how can we write? It is equal to length of the LM into power scale. Length of the LM into power scale, which is equal to 2 centimeters into 1000, that is 1000 watts per centimeter. So it is 2000 watts. Similarly, PSN is equal to length of the LM into power scale. 10 into 1000, 10,000 watts. This is a way we can calculate, we can fix actually the power scale of induction motor. Later, my assumption is the rated output power of the induction motor is 4000 watts. Then first of all convert into centimeters according to the power scale, that is vertical axis. So rating of the machine, rating is equal to 4000 watts divided by 1000 watts per centimeter, that is equal to how much it is? 4 centimeters. 4 centimeters is the rating of the machine in terms of the length. Output power or rating of the motor, rated output power of the motor, that is 4000 watts. In terms of the power scale, it is 4 centimeter line. So to find out the full load point on circle, we have to know the rated output power of induction motor. Once you know the rated output power, convert into power scale, that we have a 4 centimeter. Now we have to draw from point S a 4 centimeter vertical line. You have to draw a 4 centimeter vertical line. For example, I am assuming it as some X. Sx is equal to length of the Sx is nothing but 4 centimeters, that is equal to rated output power. Rated output power of machine. And once draw the rated output power of the machine from point S to point X, then after draw a parallel line for output. From point X, draw a parallel line for output line towards the circle. For example, I am drawing a parallel line approximately. So I am drawing a line which is from the point X, which is exactly parallel to the output line, and which met your circle at a point I am naming as P. This is a point called full load point. The point P will be a full load pointer induction motor. Now drop a line from P to x-axis. Drop a line from P to x-axis which intersect your output line at E and which intersect your torque line at F and which intersect your AB line at G and x-axis at D. Now length of the GD represents the fixed losses. Anyway, these are constant irrespective of the load current. The fixed losses are constant, but your variable losses will change. Length of the EF, length of EF, length of EF represents the rotor. Length of EF into power scale represents the rotor copper losses. Length of FG represents the stator copper losses. Right? An angle between y-axis and P will be the phi 1, the phase angle for input power, that is phi 1. Or you can also calculate the phase angle by right angle triangle, also you can calculate it. So this is the case. We can find out rotor copper losses, we can find out stator copper losses, and length of the PE represents the input power, that is output power. Is it output power? This is output power line, and this is total input power for the induction motor, and PE represents the output power, that is the input power minus fixed losses minus stator copper losses minus rotor copper losses. So length of the PE represents the rated output power of induction motor under full load condition, and EF represents the rotor copper losses, FG represents the stator copper losses, GD represents the constant losses. So once you know all these losses at a full load point, you know rotor copper losses is equal to what is the formula for rotor copper losses? Slip times of the rotor input So you can find out rotor input power is equal to rotor copper losses by S. You can also find out the slip is equal to rotor copper losses by rotor input power. We can also find out slip. And we know the input power from the circle diagram, we know the output power from the circle diagram, we know the losses from the circle diagram, we know this slip from the circle diagram. Then we can find out the efficiency of induction motor as well. And this is all about the how to draw the circle diagram for an induction motor. And here we clearly represented the efficiency is equal to PE by PD. So PE is the output power and PD is the input power. Next, and the slip is equal to EF by PF. EF, that is a rotor copper losses, by PF, that is a rotor input power. Rotor input power is equal to the stator output power. That is, we can also mention the addition of the rotor copper losses. The output power plus copper losses is equal to input power for rotor. That is why it is PF by EF by PF, and starting torque at rated voltage will be SK. That is SK. The starting torque, this is SK. And you can also find out maximum torque, you can also find out maximum power from the circle diagram by drawing a tangent normal line for circle with respect to the respective parameter. That is, if you have to draw a parallel line for torque, this is AK is the torque line. You have to draw a parallel line, that is a tangent normal line for Ka to the circle. This is the line we have. This is the line we have. This point will represent the maximum torque point. So from this point to drop a line from this point to torque line. For example, it is y. For example, it is z. Length of this yz represents the maximum torque. And similarly, you have to draw a parallel line for output power. That is a tangent normal line. That is, this is the point where it intersect your circulate, P maximum, and drop a line from P maximum to output power. So length of, for example, it is F, for example, it is G, or for example, it is M and N. It is M and it is N, for example. And now length of the Mn into power scale, that represents the maximum power output. Maximum power output of induction motor. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.